Over 4.56 billion years ago, the explosion of a star and the resulting creation and contraction of a nebula led to the formation of our solar system. All of the elements found in our solar system were created within the exploding star. Without these elements, we as humans would not exist. There would be no matter, no energy, no life. This image taken from the Hubble telescope is the Orion Nebula. Eventually, a new solar system will emerge from this cloud. This photograph of Earthrise, taken from lunar orbit, profoundly influenced our perception of Earth. We began to understand that we live on an island in the blackness and emptiness of interstellar space. As Alan Dean Mitchell, the sixth person to walk on the moon, said, it was a beautiful, harmonious, peaceful-looking planet, blue with white clouds, and one that gave you a deep sense of home, of being, of identity. It is what I prefer to call instant global consciousness. Scientific cosmology is the study of the overall structure of the universe. Matter is the substance that makes up objects, and energy is the ability of a region of space and the matter within it to do work. The amount of matter within an object is its mass. Greater mass, more matter, and the more potential energy it has. The scientific method provides the foundation to explore the cosmos, the sun, earth, and other celestial objects. Ask questions. Again, the curiosity, for example, how does water, a liquid, erode rock, a solid in streams? Collect information. Go to the library and collect all the information you can about stream erosion. Review the data. Read the information, try to duplicate the experiments that others have done, see what the differences are. State the problem. After you review, you will have a clearer understanding that most stream erosion is by physical erosion caused by saltation of rocks along stream bottoms. But that doesn't explain what occurs in unconsolidated streams that doesn't transport gravel. So the question may be, how does physical erosion occur in unconsolidated streams? Formulate the hypothesis, a statement. Stream erosion in unconsolidated stream beds occurs as a result of the shear stress water exerts on the channel bottom. Test the hypothesis. Distribute sensors in unconsolidated streams in your area, recording water height, water temperature, water velocity, and the square area of the channel to see if the forces in the stream are strong enough to overcome the resistance of the clays in the channel. Then do that in many streams under differing environmental conditions. If the tests refute the hypothesis, then modify or make new hypotheses from the results and retest. Lastly, when all the results have been analyzed, they have to be presented to the scientific community at large. This is usually accomplished by writing up your work and presenting it in a journal, such as the Journal of Hydrology, to be reviewed and retested by your peers. If it is approved, then you have added your theory to the large body of information on stream erosion. So you can see that theories are not come by easily. They are not opinions, but provable ideas that have undergone rigorous testing by you and your peers. Imagine what it would be like to not know what celestial objects are made of. Early astronomers realized that the objects in the sky had recognizable order. For example, when viewed for the whole night, stars in the northern hemisphere appear to revolve around the North Star. Other objects, when they tracked them, appeared to move relative to the backdrop of stars. How did our sense of the scale of the universe come to be? The Greek astronomer Eratosthenes, who lived from 276 before the Christian era to 194 before Christian era, came up with the first good estimate of the dimensions of the Earth. Not long after Eratosthenes' discovery, Greek mathematicians used ingenious calculations to estimate the distance to the moon. and found that it is about 30 times the Earth's diameter, 7,917.5 kilometers, or miles rather, times 30 equal 237,525,000 miles. Actual mean is around 238,855 miles. It wasn't until the 17th century that astronomers were able to figure out that the mean distance to the sun at 93 million miles. Once it was determined that the speed of light was constant, the distance light traveled in an Earth year, about 6 trillion miles, we began to truly understand the vastness of space. The Milky Way galaxy is 100,000 light years across. The edge of the visible universe lies over 13 billion light years away. So early philosophers reasoned two hypotheses to explain these mysteries of the night sky concerning the arrangement of stars and planets and their relationship to the Earth, Sun, and Moon. The geocentric view advocated by Ptolemy 100 to 170 AD stated that the Earth sits without moving at the center of the universe, while the sun, moon, and planets whirl around in circular orbits within a shell of stars. The second view, proposed by Copernicus, 1473 till 1543, advocated a heliocentric model in which the sun lies at the center of the universe, with the Earth, moon, planets, and stars revolving around it. Then during the Renaissance, thanks to the efforts of Copernicus, Galileo, Kepler, and Newton, people came to realize that the Earth and planets did orbit the sun in elliptical paths, and that the sun was not the center of the universe, but was a star among many stars with gravity, the attractive force that one mass exerts on another, holding it all together. Modern scientific cosmology is usually considered to have begun in 1917 with Albert Einstein's publication of his final modification of general relativity in the paper Cosmological Considerations of the General Theory of Relativity. Our sun is an average star among 300 billion stars in our galaxy, the Milky Way galaxy. There are smaller stars and larger stars, even up to 100 times larger. From our vantage point on Earth, the Milky Way looks like a hazy band. If we could view the Milky Way from a great distance, it would look like a flattened spiral with great curving arms slowly swirling around a glowing disc-like center. Astronomers estimate that more than 1,000 billion galaxies constitute the visible universe. Our sun's gravitational pull holds on to many objects, which together make up the solar system. The sun itself contains about 99.8% of all mass in the solar system. Astronomers define a planet as an object that orbits the sun, is roughly spherical, and has cleared its neighborhood of other objects. There are two groups of planets in our solar system. The interior, or terrestrial planets, are small, dense, rocky planets. From the sun outwards, they are Mercury, Venus, Earth, and Mars. The next group of planets are known as the gas giant planets. They are large, low-density planets, Jupiter, Saturn, Uranus, and Neptune. They are separated from the terrestrial planets by the asteroid belts. Comets and most dwarf planets exist beyond Neptune. Pluto, which was our ninth planet, does not fit the definition, and so it was dropped from the planetary list because it had not cleared its orbit. The 8 planets orbit the sun in the same direction and in the plane of ecliptic. All but 2 planets, Mercury and Venus, have moons in varying numbers. Earth has 1, Mars has 2, and Jupiter has at least 63. Asteroids are rocky or metallic objects that orbit the Sun in the asteroid belt between Mars and Jupiter. They range in size from about 1 centimeter to 930 kilometers. The dwarf planet Eris, found in 2003, is 20% larger than Pluto. Comets are icy objects that orbit the Sun beyond Neptune. An exoplanet or extrasolar planet is a planet outside the solar system. The first possible evidence of an exoplanet was noted in 1917, but was not recognized as such. Then 75 years later, the first confirmation of detection occurred in 1992. As of the 1st of October 2019, there are 4,118 confirmed exoplanets in 3,063 systems, with 669 systems having more than one planet. Earth spins on an axis of rotation. The axial tilt of Earth is about 23.4 degrees. The rotational velocity is 1,674 kilometers per hour at the equator. The Earth orbits the Sun, 150 million kilometer elliptical path. The orbital velocity is 108,000 kilometers per hour. The solar system revolves around the center of the Milky Way, 1 revolution per 250 million years. The solar system velocity is 720,000 kilometers per hour. In the 1920s, unexpected observations about the nature of light from distant galaxies led to a scientific model of the universe's formation known as the Big Bang Theory. To explain these observations, we first need to understand an important phenomenon called the Doppler effect. Discoveries in the 1920s related to the Doppler effect led to ideas about the formation of the universe. When a train whistle screams, the sound you hear moved through the air from the whistle to your ears in the form of sound waves. Sound waves are disturbances that transmit energy from one point to another in the form of periodic motion. This motion can be divided into wavelengths, the distance between successive waves, and the frequency, the number of waves that pass a point in a given time interval. Waves are divided into crest and trough. A wavelength is the distance between two troughs or between two crests. The Doppler effect is the phenomenon in which the frequency of wave energy appears to change when a moving source of wave energy passes an observer. Waves can compress or relax with relative motion. Compressed waves or shorter wavelengths means higher frequency. Relaxed or longer wavelengths means lower frequency. A stopped train sounds different than a moving train. As the train approaches a person, the person hears a higher pitch. As the train passes, the pitch drops, higher to lower. As the train recedes or goes away, a person hears a lower pitch. Moving light waves reveal the Doppler effect. Light moving towards an observer compresses or becomes blue. Light moving away from the observer expands and becomes red. A moving star displays Doppler shifted light. Approaching starlight is compressed, blue shifted. Receding starlight is expanded, red shifted. The Doppler effect influences light waves too. Visible light is electromagnetic radiation. Color varies based on the wavelength. Red light has a longer wavelength, lower frequency, and blue light has a shorter wavelength, higher frequency. Does the size of the universe change? The atoms in a star absorb certain specific wavelengths of light. We see these wavelengths as dark lines on a light spectrum. Note that the lines from a galaxy a billion light years away are shifted towards the red end of the spectrum as compared to the lines of our sun. Light from galaxies displayed a red shift compared with nearby stars. Edwin Hubble recognized the red shift as the Doppler effect. Galaxies are moving away from Earth, and no galaxies are moving towards the Earth. The expanding universe theory is the theory that the whole universe must be expanding because galaxies in every direction seem to be moving away from us. There are three possible types of expanding universe. They are called open, flat, and closed universes. If the universe were open, it would expand forever. If the universe were flat, it would also expand forever, but the expansion rate would slow to zero after an infinite amount of time. If the universe were closed, it would eventually stop expanding and recollapse on itself, possibly leading to another Big Bang. In all three cases, the expansion slows, and the force that causes the slowing is gravity. An interesting phenomenon that we see is that galaxies further from Earth are moving away faster than galaxies closer to Earth. The Big Bang theory states that all matter and energy compressed to a single point in a previous universe. And then that point exploded, beginning the creation of our universe about 13.7 billion years ago, and it continues to expand today. After that explosion, 10 to the minus 43 seconds after that explosion, the cosmos goes through a superfast inflation, expanding from the size of an atom to that of a grapefruit in a tiny fraction of a second. Then by 10 to the minus 32 seconds after the explosion, the temperatures had risen to 10 to the 27th degrees centigrade. This is called the post-inflation. The universe is a seething hot soup of electrons, quarks, and other particles. Then by the time we get to 10 to the minus 6 seconds, the universe had cooled to 10 to the 13th degrees centigrade. It's a rapidly cooling cosmos, permits quarks to clump into protons and neutrons. And then 3 minutes after the explosion, the universe was at 10 to the 8th degrees centigrade. It's still too hot to form into atoms. Charged electrons and protons prevent light from shining. The universe is a super hot fog. Then 300,000 years after that, or between 3 minutes and 300,000 years, temperatures had dropped to about 10,000 degrees centigrade. Electrons have combined with protons and neutrons to form atoms, mostly hydrogen and helium, and light can finally shine. And then about 1 billion years after the explosion, the universe's temperature has dropped to a minus 200 degrees centigrade. Gravity makes hydrogen and helium gas coalesce to form the giant clouds that will become galaxies. Smaller clumps of gas collapse to form the first stars. Then in about today, present day, 15 billion years after the Big Bang, the universe temperature is about minus 270 degrees centigrade. As galaxies cluster together under gravity, the first stars die and spew heavy elements into space. These will eventually form into new stars and planets. After about 200 million years of expansion, atoms and molecules accumulated into patchy clouds called nebula. Gravity caused the collapse of this gaseous nebula, and the collapse resulted in increases in temperature, density, and the rate of rotation of the nebula. This is an artist's impression of a protostellar disk around a recently formed or forming star. The disk will eventually disappear, but parts of it will contract to form planets, asteroids, and comets. A protostar forms when the mass becomes hot enough to glow. A star is born when nuclear fusion starts. First-generation stars were massive but short-lived. These stars existed for a few million to tens of millions of years. At the end of a star's life, it explodes to form other stars, or other nebula, and then other stars. There are 92 naturally occurring elements. During the Big Bang nucleosynthesis, the 5 lightest elements were formed: hydrogen, helium, lithium, beryllium, and boron. The next 21 elements were formed during the life cycle of stars by the process of stellar nucleosynthesis. The remaining 66 heavier elements form only at ultra-high temperatures that develop in a supernova explosion. The process is known as a supernova nucleogenesis. And of course, that's where our elements came from. The sun and all other objects in the solar system formed from material that had been swirling about in a nebula. This is known as the nebular theory or the condensation theory. The accretionary theory states that 1. Solids collected into dust-sized aggregates. 2. The aggregates collect into grainy masses similar to this lithic chondrite shown in the image above. 3. That the disk then evolved into a revolving ring of debris. And 4. The large particles collect into rings of planetesimals and protoplanets. And finally, 5, our 8 planets remained. Early on, the Earth was fairly homogeneous and plastic, with a magma ocean on the surface. When the temperature got hot enough because of kinetic energy, compression due to gravity, and nuclear decay, iron and nickel began to melt and migrate to the core, where it accumulated and formed a liquid core. This is called the iron catastrophe. How did the moon form? The giant impact hypothesis, sometimes called the Big Splash or the Theia impact, suggests that the moon formed out of the debris left over from a collision between Earth and an astronomical body the size of Mars, approximately 4.5 billion years ago. In the Hadean eon, about 20 to 100 million years after the solar system coalesced. The giant impact hypothesis is currently the favored scientific hypothesis for the formation of the moon, and the supporting evidence for this includes Earth's spin and the moon's orbit have similar orientation. Moon samples indicate that the moon's surface was once molten. The moon has a relatively small iron core. The moon has a lower density than Earth. There is evidence in other star systems of similar collisions resulting in debris disks. Giant collisions are consistent with the leading theories of the formation of the solar system. And finally, the stable isotope ratios of lunar and terrestrial rocks are identical, implying a common origin. The first atmosphere consisted of gases in the solar nebula, primarily hydrogen. There were probably simple hydrides, such as those now found in the gas giants Jupiter and Saturn, notably water vapor, methane, and ammonia. Most of these gases were probably blown away by the solar winds. However, near continuous outgassing from volcanism, supplemented by gases produced during the late heavy bombardment of Earth by huge asteroids, most likely produced an atmosphere consisting largely of nitrogen plus carbon dioxide and inert gases.